You know that box in your kitchen? What if I told you it cooks your food from the inside out using a totally invisible force? Today, we're going to pull back the curtain on how your microwave really works. I mean, think about it. It's a question we've all had, right? You pop in some cold leftovers, fit a button, and just a minute or two later, it's steaming hot. There's no fire, no glowing red element. So what in the world is going on in there? Yeah, it's such a normal part of our lives that we don't even think about it. But behind that simple little box is some seriously cool physics and engineering. The secret has a name, and it's called dielectric heating. It sounds complicated, but it's really just a powerful way of turning electromagnetic fields into heat, and it all starts at the molecular level. So, to really get how this works, we need to zoom way, way in and check out the core science. I like to call it the dance of the molecules. So here's the official definition. Dielectric heating is all about using high-frequency electric fields to heat up stuff that has polar molecules. And it just so happens that the most common polar molecule on Earth is the main ingredient in pretty much all our food. Yup, it's all about water. You see, a water molecule isn't perfectly balanced. It's got a slightly positive end and a slightly negative end. This makes it act like a tiny, microscopic magnet. And that one little fact, that's the key to everything. Okay, so here's how that dance plays out. First, the microwave generates an electric field. All those tiny water magnets immediately snap to attention and line up with it. But then, and this is the magic part, the field flips. And it keeps flipping back and forth about 2.5 billion times every second. The water molecules just desperately try to keep up, spinning around like crazy and bumping into each other. All that frantic motion, all that molecular friction, well, that's heat. It's why foods with a lot of water, like your veggies, cook so much faster than drier things like bread. Now, you'd probably assume that to do this job, a microwave would have to be tuned to the absolute perfect frequency for water to absorb energy. But here's the thing that's really interesting. It's not. It's not even close. Just look at these numbers. Your home microwave zaps your food at 2.45 gigahertz, but the best frequency for water to soak up that energy is way up around 10 gigahertz. So why the huge gap? Is your microwave just bad at its job? Well, it turns out this is actually a brilliant bit of engineering. It's a feature, not a bug. See, if the frequency were perfect, all that energy would get absorbed by the very outer layer of the food. You did a burnt crust and a frozen middle. By using a less perfect, less absorbent frequency, the waves can actually travel deeper into the food, spreading out the heat much more evenly. Pretty clever, right? But this tech isn't just for reheating your leftovers. The same basic idea, dielectric heating, is used on a huge industrial scale, but it works a little differently. The other big player here is radio frequency heating, or RF heating. Now, RF uses a much lower frequency than your microwave does. Just think of it this way. A lower frequency means a longer, more powerful wave that can penetrate way deeper into materials. It also creates a whole different kind of heating field. Your microwave is far field, kind of like feeling the warmth from the sun's waves. Industrial RF is near field, which is more like putting something directly between two hot plates. It's perfect for those big industrial jobs. And this capability has basically powered an invisible industrial revolution. I guarantee you've used or eaten something today that was made with this technology, and you probably had no idea. So yeah, this is not your kitchen appliance. This is an industrial RF heater, and it is an absolute workhorse. It uses that deep penetrating energy to do things that would be super slow or even impossible with regular old heat. And the things it's used for are all over the place. RF heating cures the glue in the plywood that builds our houses. It dries gigantic stacks of lumber. It even kills pests inside walnuts after they've been picked. And in the food world, it's used to get that perfect final crispiness in biscuits and cereals, which can boost an oven's output by more than 50%. And believe it or not, this isn't some new idea. This quote is from the original patent filed by Bell Labs way back in 1937. They knew, right from the very beginning, what the biggest advantage was: the power to heat something all the way through, all at the same time. But the story doesn't stop with food and furniture. Some of the most amazing and important uses for this tech are in medicine and, get this, art history. So in medicine, doctors use RF heating and a thing called diathermy, which warms up deep muscle tissues for physical therapy. And if you crank up the temperature in a very controlled way, a technique called hyperthermia can use that same focused energy to target and kill cancer cells, which often makes other treatments work even better. And this is where it gets truly mind-blowing. This invisible heat, born from the same idea that warms your cup of coffee, is now being used to save priceless pieces of our history. Just imagine a masterpiece carved from marble, something like Michelangelo's David. For hundreds of years, art experts have been fighting a losing battle against microscopic fungi that slowly eat away at the stone. Well, now they have a new tool in their arsenal. Researchers figured out that targeted microwaves at the exact same 2.45 gigahertz frequency as your kitchen oven can gently heat the surface just enough to kill off those fungus colonies without doing any damage to the delicate marble itself. It's a way to protect art for future generations without chemicals and without even touching it. So from reheating your dinner to building our homes to fighting cancer and even saving Renaissance sculptures, this invisible force is literally all around us. It really makes you wonder, what other problems could we solve if we just found the right frequency? What will we heat up next?